Hi, this is Harshavardhan. I'm here to present the paper using transformers to learn dictionaries and representations on behalf of me and my co-author Aditya Srivastava. This paper was submitted to the SemEval 2022 Task 1, comparing dictionaries and word embedding. The abstract, we propose a pair of deep learning systems which will effectively learn representations from dictionary definitions. This was named the reverse dictionary subtask. The second subtask was named definition modeling subtask, where we generate dictionary definitions given the representations. So to do so, and to create the systems, we exploited the latest techniques that are present in the NLP systems, like unsupervised pre-training, attention mechanisms used in transformers, multitask learning to optimize over multiple losses, and also contrastive learning to make use of negative samples to improve our scores. Our systems achieved competitive performance on the reverse dictionary subtask and and the definition modeling subtask for English language was placed first among all the submissions. Word embeddings to introduce a problem statement, word embeddings are said to be real-valued vectors that encode semantics of a word. They have significantly improved performance on various downstream NLP tasks like question answering, natural language understanding, and most NLP tasks, to be honest. So, do word embeddings encode semantics similar to a dictionary? So, a dictionary encodes semantics by giving us a definition. So if word embeddings encode semantics similar to a dictionary, then we should be able to generate definitions from these word embeddings of vectors, and we should be able to generate vectors from these definitions. So uh, to pursue this, the creators of the shared task have proposed a problem statement with these two subtasks: reverse dictionary, where we reconstruct embeddings from the dictionary glosses or definitions, and definition modeling, where we reconstruct glosses from their embeddings. So, the provided dataset contain dictionary glosses in multiple languages. We limited ourselves to English. And for each gloss or definition, there are three corresponding vector representations provided. One is the word embeddings using word2vec. Second are the character embeddings. And third are the electro embeddings. Moving on to the first subtask, the reverse dictionary task. So here, given a gloss sequence is the definition that is provided. Using this, we need to generate the three respective embeddings. So this subtask consisted of three smaller subtasks, which were generating the cosine embedding, generating the character embeddings, the word-to-vec embeddings, and the electro embeddings. So the output vectors should be these three. So we have three separate systems for each of these three subtasks inside reverse dictionary. So to encode these definitions, we have a transformer encoder which consists of 6 layers. So initially, this transformer encoder is pre-trained on mass language modeling uh, task, which is unsupervised in nature. We did this in order for the transformer encoder to have a good enough prior to start predicting the proper vectors later. So then we fine tune this with a combination of a cosine embedding loss and a mean squared error loss. So these two were first initially put in place because MSE approximates the vector to the goal vector, and cosine embedding makes sure that it is semantically close to it. But to also make sure that the generated vector is also distant from semantically non-similar words, we also put in a contrastive loss where negative samples from the dataset are picked up and the distance between them is made sure to be larger so that negative samples are like farther from the actual correct samples. So the metrics used to judge this task were mean squared error, uh, cosine similarity, and cosine based ranking. So cosine based ranking was to rank the predicted with all the other possible word vectors and to see how the test items have ranked. So the negative sampling was introduced in order to have a better cosine based ranking. So these are the best submissions that we have. We can initially when we tried only with cosine embedding, we had a very good cosine similarity. In each case, we can see that cosine embedding loss gives the best cosine similarity metric, but MSE is affected hugely. So once we introduced the pre-training and the multitask objectives, we saw an improvement in performance with respect to all the vectors. To see that here, we can clearly see that using only MSE gives the best MSE performance, and using only cosine embedding gives better cosine embedding performance. But using all the combination of all the losses will give us the best metrics for each vector, and this trend can be observed for all the three types of vectors. Moving on to definition modeling, here the three types of vectors are provided to us, and our task is to generate the actual definition. So for this text generation task, we have used a transformer decoder model to model this, where we have modified the cross attention part of it. So in the cross attention, so in a vanilla sequence to sequence model, the output of an encoder is taken, but here we have taken the output by creating a feature vector by concatenating all three vectors and having a linear transformation over it. So this feature vector is passed on as uh, to project into keys and values, and the query is taken from the output of the self-attention layer. So the outputs of this transformer decoder are have a softmax layer at the end where the probabilities are predicted, and using this, the words are generated for the definition. So the metrics used for this task are a mover score. This is a more recent implementation using transformer-based models, which provides a mover score, a blue score, which is more of a surface level score, and here it is termed as S-blue. And a lemma-based blue score is also introduced because in cases like word to vec in character, a single input may have multiple targets since sense is not encoded in it. So it is computed for all possible 50 words, and then a maximum is taken. So this is the lemma-based score. So here we can see that it is to account for the same input having multiple targets in case of SGNS and character level. So we can look at the def mod scores here. We can see that Electra, potentially being the most recent form of encoding, uh, has we can see that it provides the best scores for S blue movers as well as L blue. This can be we can draw a conclusion that Electra might possibly contain the most information of all the three, but we can also see that concatenating all three also gives us a better score, indicating that the other two also encode information that is not present in Electra. Looking at some of the examples that are actually being generated, we can see that farming is the word. So these words were released post the competition ended. Initially, we were having access only to the vectors. So for the word farming, we can see that a farming operation is the gold clause that is given. The model predicted the act or process of producing food. For hardware, for example, the golden clause is equipment, but the model predicts offer relating to a computer system. So this way we can see that it understands meaning. It also predicts some negative examples as shown here. From some of the analysis, we can see that the model shows a remarkably good mapping between words and their representations and makes close approximations of their meanings. So we can see that from the farming example, where even though food is not being given as an input in the gold form, it is still making a relationship between food and farming. The model also tends to learn definition templates such as of pertaining to or related to. So, for example, in the chesty example, uh, even if it does not know the definition, it just prints something in the form of pertaining to. Even in Solarian, it generates offer pertaining to in order to make it seem like a definition so that the cross entropy loss decreases. And it also, being a sequence to sequence model, also generates some degenerate output where it repeats some of the words. In conclusion, we can say from common observations that multitask learning over all three vectors outperforms, and unsupervised pre-training also include our scores. We would also like to explore how pre-training on external data improves our results in future work, such as pre-trained language models, and we would also like to take into account a GAN-like approach where both the models can be trained simultaneously so that they can learn from each other.